Okay, hello. My name is Evgeny Burnaev. I'm head of Intellectual Data Analysis Department. And today I'm going to present you how to add value to your experimental data and how to perform faster system behavior prediction with surrogate modeling in pSeven. Do you hear us well? Do you see us well? If no, please write about these problems into the chat and write this to the host. So the host will solve your problem. Okay, I hope that everything is good, and now we will continue with this presentation. The presentation contains several topics. First of all, I will give you some motivation. Why do we need surrogate modeling? What capabilities in pSeven we have for surrogate modeling? How to perform surrogate modeling for variable fidelity data, namely how to perform data fusion, and some conclusions. Okay, so what is pSeven? pSeven is an integration platform for automation of engineering simulation and data analysis. 2. Reduce design time by decreasing number of expensive experiments and computations needed for analysis and optimization. To improve product performance using advanced optimization algorithms. And to understand the most important cost and performance factors. pSeven includes macros library containing generic tools for multidisciplinary optimization, design of experiments, dimension reduction, and surrogate modeling. And today we will give you the most important information about capabilities for surrogate modeling. Let me give you some motivation about why do we need surrogate modeling. Let us imagine that we have some object, for example, airplane, and this object is described by a vector of some design characteristics like geometric configuration of wings and other parts of the airplane. And we have vector of object characteristics corresponding to the considered object design. For the case of airplane, it can be lift and drag coefficients and other aerodynamic coefficients, some other performance criteria values, etc. And we have the rule which maps the vector describing object design to the vector of characteristics. And in the considered case, it can be some computational fluid dynamics code, or it can be experiments in one tunnel performed with an airplane model, or it can be some other physical model. And well, the goal of the usual goal in such case is to find an object with optimal characteristics. That is, we need to optimize the design of the object such that the corresponding criteria are optimal. But well, very often, especially in case the object is complex, like airplane, in order to find characteristics of the object with some fixed design X, this task is very expensive in terms of time or money. So, but it may happen, and it's often the case, that from previous experiments with computational fluid dynamics code, from previous experiments and wide tunnel database, etc., you may have some data table consisting of some data like the one given on this slide. For example, you may have some columns corresponding to inputs like values of angle of attack, values of Mach number, etc. And you already obtained some measurements of output values like lift coefficient and other output values. And this data table is rather difficult to obtain since each evaluation of the function f of x is expensive or time consuming. But you have some database. Well, what you want to do? You want to either find, estimate, evaluate some characteristics y sub n plus 1 for some new object description x sub n plus 1 using observations already obtained. Or you may want to find an object with optimal value of output characteristics. And you have this database. It consists of inputs. You see the table on the picture, consisting of two parts. It's inputs and outputs. And the whole table in data analysis is usually called as training sample. So, and as already said, it's expensive to calculate the values of f of x for new values of x. Are there any alternatives to direct computation of the value of this function? Well, in fact, yes. You can use surrogate model of this function. What is surrogate model? Well, surrogate model is some mathematical function which is constructed using only the already obtained database, the already obtained training sample, and surrogate model is fast and cheap to evaluate for new input vector, and it is constructed in such a way such that it's close to initial function. On the left, you see the training sample consisting of some data points, and on the right, you see the corresponding surrogate model, which is some mathematical expression representing the initial dependency. Let me give you some examples how the surrogate models can be used in real engineering problems in order to speed up the optimization or modeling of physical phenomena. In this case, on this particular slide, we see some example of structural optimization task. We want to minimize the mass of the complex composite structure subject to strength constraints. Namely, we have some structure, and this structure is characterized by reserve factors. Reserve factors are giving you information on whether the structure is strong enough or not. If reserve factors are greater than 1, then the structure is strong enough and it can be used. So, but the problem is that in order to analyze the strength properties of the composite structure, you need a lot of computations, and it's very slow. And reserve factors, the dependence of reserve factors on object structure, it's rather noisy, it's rather discontinuous, and that is why if you use original physical analysis code, then optimization of the structure may take very lot of time. But if you want to speed up the optimization, you may replace original analysis code with accurate and smooth surrogate model, and this is the case in this particular problem. And when we replace the original analysis code with the surrogate model, it turned out that the surrogate model was very accurate, and its error was like about 1%, and it turned out that the whole optimization process we succeeded to speed up the whole optimization process for up to 10 times, from several weeks to several days. Another example of why we need surrogate models is that we may need to be able to estimate some important output characteristics for new objects. Let us consider an example how to estimate loads from flight configuration parameters. And the objective is to estimate loads for missing flight configuration parameters using existing database of helicopters loads. The problem here is that there is no physical model for predicting missing loads, and the analysis of the missing loads requires a considerable amount of manpower and time, since you need to perform real experiments with real helicopters. But if we gather some database of existing loads and construct the surrogate model using these existing loads, then for a lot of different cases of missing loads, we can calculate a lot of for a lot of cases of different flight configuration parameters. We can calculate missing loads with very good accuracy, sufficient for engineering applications. And this can be done only due to we use surrogate models. So here I present you two very important examples of surrogate model application. They motivate why we need surrogate models. I hope you are motivated now to use our surrogate modeling capabilities. And now I will give you some details on which functionality we have for surrogate modeling. Well, in general, approximation process in pSeven, it can be represented by this diagram on this slide. We have some training sample. It is just some table with numbers of values of inputs and outputs. Well, you load this training sample into pSeven using a special block called CSV parser. Then you input this database to builder, which constructs the surrogate model. Also, you give as input to this builder some high-level parameters like whether you need exact fit, whether you need accuracy variation. I will comment on these features a bit later. So you specify these high-level parameters. It's some properties of the surrogate model you may want to have, and after that, builder constructs the surrogate model, taking into account these required properties and using the database. Okay, inside the builder, in fact, we developed a list of approximation techniques, which corresponds to state-of-the-art techniques, as well as we implement some in-house methods. Theoretically proven. And of course, in general, engineers don't want to know a lot of details about data analysis, machine learning, and such things, and don't want to get into details how to select parameters of a surrogate model construction process. So what to do? How to select the best technique? Fortunately, for this, we have a special decision tree based on a lot of experiments, a lot of simulations, some theory, and this decision tree, depending on features of the sample, depending on dimensionality of data and the user-specified options, select the best technique for the considered particular case. On the picture to the right, you can see some part of this decision tree. It's very complex, and it will do the work for you. Some example of which particular feature of the data sample we take into account. For example, we take into account whether the sample has a special structure. In particular, we check if the design of experiments, that is, input vectors, are located in the design space according to full factorial design of experiments, or according to incomplete factorial design of experiments. Example of full factorial design of experiments you can see on the left on the picture, and of incomplete factorial design of experiments you can see on the right. And if one of these two cases is presented in the data, then according to the decision tree, a special technique for processing of such data is selected. It's a special in-house method which provides very flexible model with low training time, even for very large training samples up to several millions. And it can handle non-uniform designs in a very efficient manner and very accurately. Okay, so after the decision tree selects the best possible method, then the surrogate model is constructed. Now let me comment on the setup of surrogate model. Okay, sorry guys, it was some technical issue, but now we will continue. So just a second, I will show the full screen mode. So already said, we want to set up the surrogate model features we may want to have. And now I would like to comment on the surrogate model features first of all, we can specify whether we want exact speed or we don't want exact speed. Well, if we want exact speed, this means that we want to have an approximation which goes through all the training points exactly. It may be important if your data is very very precious, I would say, and you want your surrogate model to go through all the points you have. But you should be careful if your data is noisy. So if your data is noisy, you may want to smooth your data. That is why it's better not to use exact turned on. Another feature which is important is the feature called smoothing. If your function is noisy, if your function is continuous, then the approximation will approximate the function and also will be discontinuous and noisy. That is why you may want to additionally smooth your function, to smooth your surrogate model in order to use, for example, your surrogate model inside some cultural law. And for this, you may use smoothing capability. Okay, so now I would like to tell you one of the most important things. Namely, how to check whether the surrogate model is accurate or not. Because, well, when you construct a surrogate model, you may want to check if it can be really used to perform prediction or not. And there are several methods how to check the accuracy of the surrogate model. First of all, you may want to you may estimate error on the trained sample. You may estimate error on independent test sample, and there are also two special options called internal validation and accuracy evaluation, which also can give you ability to additionally estimate the accuracy of the surrogate model. First of all, in any case, accuracy of the surrogate model, average accuracy of the surrogate model is estimated by different error quality measures. Example of error quality measures you can see on this slide. It's first of all mean absolute error, root mean squared error, relative root mean squared error, and you can use also some other types of errors as well. But in order to estimate these errors, you need some data. So first of all, of course, you can use the same training data which you use in order to construct the surrogate model. In such case, you should be very accurate. Why? Well, because basically error on the trained sample underestimates through error. This phenomena is called overfitting phenomena. Namely, if you look on the picture to the right, you can see example of an overfitting phenomena. You see the true function which is given by red. You see its approximation which is given by blue, and the trained sample is depicted by green points. And if, for example, your approximation is going through training points exactly, then if you estimate the error on the trained sample, then this error will be 0. At the same time, if you calculate error in intermediate points, then the error in the intermediate points will be not 0. That is why the most accurate way to estimate error of the surrogate model is to use the test sample. Another way how to evaluate uncertainty in your surrogate model is to use accuracy evaluation functionality. Accuracy evaluation functionality provides estimate of the accuracy of constructed model at the given point. In some sense, it's a local measure of uncertainty of the prediction obtained by the surrogate model. Accuracy evaluation characterizes the expected value of the error of approximation, and you may use this expected value in order to construct confidence intervals for your prediction. The last but not the least, the way to estimate accuracy of the surrogate model, if you don't have independent test samples and you want to somehow to estimate the average error of the whole design domain, well, this approach is called inside macros as internal validation, and this approach is can be described as follows. So you don't have an independent test sample, but what to do? You can do the following thing. You can split your training sample into subsets, then train surrogate model on subset and test the surrogate model on the last on some piece of data you selected. Calculate errors using this piece of data and perform the process, the same process with all pieces of data you already have. And then estimate average obtained error values over all pieces of data. And this error will approximate the generalization error, which can be accurately estimated using independent test sample. So if you don't have independent test sample and you want to accurately estimate generalization ability of your surrogate model, well, you should use this approach. Okay. And okay, and let me comment about the last but not the least possibility how to estimate the quality of the surrogate model. This possibility is called internal validation. So assume that you don't have independent test sample. In order to estimate the training, in order to estimate the accuracy of the surrogate model in such case, you may use the following approach. You split the trained sample into some pieces of data. You train surrogate model on all pieces of data except one. Then estimate error of approximation on the selected piece of data. And then you repeat the same process over all pieces of data. And then you average errors of approximation over all pieces of data. Finally, you obtained rather accurate estimate of the generalization ability of your surrogate model, which is rather close to the estimate obtained using independent test sample. So this is the possibility to estimate error of approximation of your surrogate model if you don't have independent test sample. And this approach is developed. It can be used automatically. You just need to switch on internal validation capability of macros library, and then the tool will do everything for you. And also let me give you some features which significantly differentiate macros library from other similar libraries, from other similar approaches for surrogate modeling. First of all, we have some special techniques to process important kinds of data. For example, mixture of approximation. It's a special approximation technique designed for clustered data and discontinuous function. We have approximation techniques which can process data with a special design structure. We can provide exact fit. We can smooth surrogate models. We can construct surrogate models with multidimensional output. We support large sample sizes and large dimensionality. We are able to specify weights for different samples. We can control the training time, and very important thing, we can export our models to C and octave source files, so you can use obtained surrogate models outside the macros library. Even you can integrate these surrogate models into your control systems, into your embedded systems, and it will fastly calculate the predictions for you. Okay, and now my colleague Yermek will present you some demo about how to perform surrogate modeling inside pSeven, and show you that it's very, very easy and very efficient.
Hello, everybody. In the first demonstration, we will show you how the approximation problem can be solved in pSeven. Let us consider the real-world problem of estimating helicopter loads from flight configuration parameters. In this problem, as inputs, we have some helicopter characteristics like its weight, altitude, and so on, and also some external air characteristics like its temperature. All in all, there are 9 input parameters, and we want to approximate 2 outputs. They are static and dynamic loads. The sample size is not large. There are 85 points. However, our pSeven is able to provide a surrogate model of sufficient accuracy, which then can be used to predict missing loads and for the specification. Okay, now let's open pSeven. Here is our workflow, and I have prepared one Python script block. This block calculates some types of errors. They are mean absolute error, root squared mean error, and relative root mean squared error. Okay, now the first thing we have to do is to load all the data. For this, go to the block library on the left panel and find the CSV parser block. Drag and drop it to the workflow. Let's name it train data. Okay, double click on it and provide your training data. Here you can choose the delimiter, and on the bottom you can see the preview of your file. Click OK. And the file we have loaded have first 9 columns that correspond to inputs, and the last 2 columns is output. So we have to divide them to these. For this, we have the submatrix block. So connect the train data block to the submatrix block like this, and you see that the pSeven automatically connect the blocks, the input and output ports with the same name. Press OK. Now open the submetrics block and add two submetrics. They will be X sample, the columns from 0 to 9, and the second submetric will be X sample, columns number 9 to 11. Press OK. The next step is to add a prox builder. Find it on the block library and drag and drop the workflow. Okay, and pass the data from submetric to the builder. pSeven connects the needed ports automatically if they are named correctly. Press OK. So the next step is to set up the builder. We will use all the default options except the internal validation, which we will use to check the quality of our surrogate model. And we have also to set up two other options. They are IV subset count. This is the number of subsets into which the training sample will be split. And the IV training count option, it is the number of the subsets that will be used for train and validation. Set them to 10, press OK. Now add to the workflow a prox player block. It is responsible for predicting values using the constructed surrogate model. Pass the model from a prox builder to a prox player by connecting them and pressing OK. Now we have to load the test data. For this, add CSV parser to the workflow. Let's name it test data. Okay, and choose the file with your test data. Choose proper delimiter. Press OK, and split the data as we did it when we load the train data. Okay. First submetric, we'll name it X. The columns from 0 to 9, and the second submetric will be Y. Columns from 9 to 11. Okay, and now pass the X test to the approx player. The last step is to calculate errors. For this, to the calc errors block, pass the output of approx player. So this connect output port F of approx player to the input port prediction of calc errors block. Also pass the calc errors block the true values, Y test, and the training values, Y train. Okay, the workflow is ready. Now we have to configure it in order to save the values we want them to analyze. For this, in configuration workflow, in the monitoring tab, add the ports that you would like to analyze them. In our case, it is the output of approx player, the predictions, the calculated errors, and also the true values. We will use them to plot some graphics. Okay, now to run the flow, press this green button. Here on the bottom on console, you can see the log. That is the message that pSeven writes to to know what steps are being performed at the moment. Here we can see the options that were used and some other useful information. Solver float finished without errors. Now to analyze the result, let's switch to analyze mode. Create new report, and what can we see here in project database? These are the results of our last run. Here we can see the modeling 4, and in modeling 4 we can find the internal validation results. Here we can see different types of errors calculated. Let's look at component-wise RRMS. You can see it is 0.16 for the first output and 0.26 for the second output. This error is sufficient in this problem for practical use. So now let's plot some graphics. For this, choose the data series you want to plot and drag and drop it to the data series window. So now to plot the graphics, choose the desired data series, and then choose the type of graphics you would like to plot. Now we will plot the scatter plot metric, that is the true values with prediction plot, and this will be two-dimensional plot. Here it is. So you can see that the points lie close to the y equals x line. This means that approximation is rather good. Now let's plot the same graphic for the second output. So it is, as you can see, looks worse, but it is still, the quality is still sufficient. So that's it. Let's return to our presentation, and I will give board to my colleague Evgeny.
Okay, so this is it for demo, and now we are going to describe you another capability for surrogate modeling, using which you can construct surrogate models on basis of variable fidelity data. Namely, you can perform data fusion. So, as already said, there can be variable fidelity data. Namely, you may have data generated by some computational fluid dynamics codes, or you may generate data from experiments from white tunnel. And there can be two types of surrogate modeling. Namely, you can construct a surrogate model using one data source. For example, you just take computational fluid dynamics data and construct the corresponding surrogate model. Or you may construct the surrogate model using data from different data sources and combine pros and cons of all available data sources in order to obtain as accurate surrogate model as possible. So let us assume that we have some low fidelity function. It's cheap but less accurate, and because of this, you can construct a bigger database. But since the database is bigger, you will get a better designed domain cover. And this function can be realized by different data sources like computational fluid dynamics code with coarse mesh, like full potential equation solver, like numerical simulation. And also you may have some high fidelity function which is accurate but more expensive to evaluate. Because of this, your database will be of smaller size. And of course, because of this, you will get worse design domain cover. Examples of data sources realizing this function are CFD code with fine mesh, earlier equation solver. It can be full-scale experiment. And a goal of data fusion is to combine strong points of different data sources. Or extract some information from the low fidelity model to complete the high fidelity data in all the design space. And we will give you some examples of such approach. But before considering the example, let us consider the typical workflow, which can be easily realized inside pSeven in order to perform data fusion. For example, first of all, you load high fidelity data, for example, white tunnel test results. You load this data into high fidelity data CSV parser. And also you load data, low fidelity data in the form of some table to another CSV parser. So you load both data of both fidelities, and then you give this data as input to builder for data fusion. As in the case of approximation, you set up required features of the builder. In fact, these features are exactly the same as for the previous surrogate modeling capability, and we also developed here a decision tree which selects the best possible method in order you are not getting into details with data analysis and machine learning. After you specify requirements for the surrogate model, the tool automatically constructs the surrogate model for this variable fidelity data and generate it inside the player, which can be used to perform predictions for new inputs. But there is another big difference with usual surrogate modeling capability, namely, you may use inside the low fidelity data sample, you can use a lightweight black box. I mean, you can use some black box function instead of low fidelity data sample, and if this black box function is rather cheap to evaluate, then the tool automatically will generate by itself a low fidelity data sample and also integrate this black box function into the constructed surrogate model, such that when you will be performing prediction for any new points, the tool will on the fly evaluate the black box function and update your surrogate model on the fly with the new evaluated low fidelity value, and this allows to significantly increase the accuracy of the prediction, because you, for any new input point, you will use updated value of the low fidelity sample. This is two types of data fusion. I described workflows for them, These are two main differences with usual surrogate modeling capability. You have data of different fidelities, and you may use the black box function instead of low fidelity data sample. And now let me give you some real engineering example which motivates why we need data fusion problems. Objective is to estimate aerodynamic characteristics of the vehicle for the different flight conditions and vehicle configurations using wide tunnel data, which is high fidelity, and CFD data, which is low fidelity. And the problems here are that high fidelity data doesn't cover some regions of the design space. Design of experiments are significantly irregular because design of experiment here is a mixture of non-uniform grids. You can see to the right example of design of experiments. So on some parts of the grid you have low fidelity data sample, on some parts of the grid you have high fidelity data sample. And what you want to construct the surrogate model using this data of different fidelities, and to perform data fusion based on approximation techniques and this kind of domain. And fortunately, due to special capabilities of macros library, even for such non-regular sparse data, you can obtain very accurate and robust surrogate model, which provides accurate behavior even in regions without a lot of high fidelity or low fidelity data. So it even can provide good extrapolation capabilities. And now my colleague will give you some example on how to make a data fusion. So here on this slide you see some description of this example. So my colleague will now give you details.
In the second demonstration, we will show you how to construct black box based data fusion surrogate model. For this, let us consider the toy problem. The high fidelity function is a one-dimensional function which has this formula, and we will use the sample with 5 high fidelity points. For low fidelity function, we will use some simple modification of high fidelity function. So, and in this demonstration, we will also show, we will compare the black box based data fusion approach to some simple approach where the points of high fidelity and low fidelity data are simply merged together and then used to construct an approximation. So now let's switch to pSeven. Go to edit mode. I have prepared some part of workflow. There are low fidelity black box function. It is a simple Python script with formula for low fidelity function. There are also 2 blocks which load the input and the output for high fidelity data, the X and Y of merged data, and also 2 blocks which load the test data. Now to construct data fusion builder, find the corresponding block in the block library and drag and drop it to the workflow. Okay, double click on it, and here choose the black box based mode. All the other options will be the default option. Now pass the high fidelity data to the data fusion builder block. So X data must be connected to X high fidelity sample port. The Y data must be connected to the F high fidelity sample. And now we have to connect the black box. So the black box should provide to the data fusion builder outputs. They are F low fidelity input port. And we should also make the reverse connection, as data fusion builder provides the input sample for the low fidelity, and we should connect XLF output port with X input port of low fidelity black box. Okay, now let's add the data fusion player. This block will perform predictions of data fusion surrogate model and make connection from data fusion builder to data fusion layer. Now let's construct the approximation of merged data as we did it in the first demonstration. So connect X sample, connect output sample, okay, and add approx layer block. Make corresponding connection, okay. And what we want else is to calculate prediction at test points. So connect X test block to our players and to data fusion player. Okay. Now go to run mode and configure workflow to save the ports with the data that we want to analyze. Then we want to save our test data. We also want to save the predictions of approximation and data fusion surrogate model. And we also to plot the training points, high fidelity inputs and outputs. And also we would like to plot the low fidelity points that were used to that were used to build the approximation. Low fidelity black box X and Y. Okay. And the one thing we forgot to do is to specify the lower and upper bounds for the low fidelity black box. We will set them as the parameters of our workflow. For this, in workflow configuration, choose parameters, choose data fusion builder block, and check the low bounds and upper bounds, and click add button. Okay, and now in run mode, here in the bottom we should set the lower and upper bounds. In our case, they are 0 and 1. Okay, so we're ready to run our workflow. Press play button and wait till the workflow is over. So here in console window, we can see the log messages. So the moment the work code is finished. Now let's go to analyze mode and plot some graphics. Create new report. Now choose the last data set. So first of all, let's plot the training data. For this, drag and drop high fidelity X and Y to data series window and plot 2D scatter plot graphic. Let's tune it a bit. First, let's move our legend to the upper left corner and give it the human readable name. For example, high fidelity data. Okay. Now let's plot the low fidelity data. Drag and drop low fidelity black box X and Y, and on the plot press the configure button, and then press add line, and add the data for the graphic, low fidelity black box X and Y. So draw on the lines, give it line name, low fidelity function, then press OK. So here are low fidelity function. Now let's plot the result of approximation on the merged data. For this, drag and drop approximation prediction and add test and data to the data series window. Then add it to the plot, press add line, and choose the correct X and Y. Let's call it merged approximation. Okay. So as you can see, the approximation is bad. It tries to approximate the high fidelity points and low fidelity points. So between the high fidelity points, the approximation goes through the low fidelity points, and this is very, very bad approximation of our high fidelity function. Let's plot the high fidelity function to see the difference. Okay, add another line, X test and the Y test. This is the true function. Okay. So now you can see the difference. And now let's plot the data fusion surrogate model. Drag and drop data fusion prediction to the data series and add it to the plot. X test matrix data fusion pair F. Okay. As you can see, the data fusion surrogate model passes through the high fidelity train points, and between them it tends to catch the trend of low fidelity function, but doesn't approximate it, and as a result we obtain the more accurate surrogate model. So that's it with demo. Let's return to our presentation.
Okay, here it is me again. It was a presentation about how to perform data fusion when you have high fidelity data sample and low fidelity black box. And now I will make some conclusions and give you insights about other possibilities with pSeven. First of all, in order to construct accurate surrogate model, you have to perform design of experiments. You have to perform sensitivity and dependency analysis to make to select the most important input features to estimate uncertainty. You need to perform dimension reduction. These tools are subjects of our future seminar webinars. And here we provide only some short description of these tools. First of all, design of experiments. It is a special tool to develop a sampling plan. To control the process of surrogate modeling via adaptive sampling, and from adaptive sampling, you will benefit most to the quality of the model while keeping as low sample size as possible. And you can reduce the number of experiments or simulations needed to reach the given quality of approximation. And this is why it's very important to use design of experiments to before generating your sample. Sensitivity and dependency analysis is a special tool which allows you to check whether there is dependency between inputs and outputs. If this dependency exists, you may filter which inputs are important and informative in terms of output prediction and which inputs are not informative. Then you may use sensitivity analysis in order to select which input features affect output the most. And using this information, you may rank informative features such that the first will be features which influence the output the most, and then features which doesn't influence the output very significantly. And after that, you may select features which provide the best approximation, because even the feature influence the output slightly, it doesn't mean that it should be obligatory taken into account when constructing a surrogate model. That is why we have a special tool which can automatically select the most important features. And the last but not the least tool, it's a tool for dimension reduction and feature extraction. If you have some object description geometry, if you have some multidimensional data, this tool allows to automatically reparameterize your data points with a smaller number of parameters. And even if you parameterize your object with a small dimension like 1, 2, or 3, you will be able even to visualize your high-dimensional data to see some clusters, some structures inside your high-dimensional data. So you can do all this with this very important tool. But as I said, these tools are topics for future webinars. Today we had a very important discussion about surrogate modeling capabilities inside pSeven. I hope I motivate you a lot about engineering applications of surrogate modeling, and we showed you that it's very simple inside pSeven to construct a surrogate model. So benefits of using surrogate model: you can predict behavior of complex systems. You can reduce time needed for analysis and optimization by replacing heavy physical model with lightweight surrogate models. And pSeven have the following features and important capabilities for surrogate modeling. First of all, it's wide variety of approximation and data fusion techniques, including in-house developed methods. It is an intelligent mechanism for automatic selection of the most appropriate technique. It's a set of advanced options for tuning surrogate models. So if you're a specialist, if you know data analysis and machine learning, you can go deeply inside to tune the surrogate model construction process using a various number of different parameters. And of course, you can the tool provides you accuracy evaluation capabilities to assess the accuracy of the surrogate model. So this is it. My colleague will give you some information about future webinars. This information will be given by inside chat. And if you have any questions, also please submit these questions to the chat, and then we will answer these questions with pleasure. Thank you very much for your attention.